Hey everyone, so today we're going to go over a very important concept in computer science known as recursion. This concept is based generally on the notion that a certain problem could be solved by solving smaller instances of the same problem. A common example of this would be computing a factorial. So remember from your math classes that a factorial of a given integer is the product of that integer and all the integers below it down to 0. So the factorial of 4 would be 4 times 3 times 2 times 1. And the common notation of this, just in math, is 4 with an exclamation point next to it. But really, that exclamation point is just a factorial. So, really, we can think of this 4 times 3 times 2 times 1 as being equivalent to 4 times the factorial of 3. And that is really the same as 4 times 3 times 2 factorial. And again, that's just the same as 4 times 3 times 2 times 1 factorial, which is going to just be 1. And so we can think of this is that we can actually solve this recursively. What I mean is that you can obtain the larger solution, which is 4 factorial, by recursively solving the smaller instances of it, 3 factorial, then 2 factorial, and then 1 factorial, but really up this way. We solve 1 factorial, 2 factorial, 3 factorial, and then multiply by 4. So this is what we're going to implement today, and we're going to use a recursive function, and of course we're going to do it in Python. So let's see how we would do that. So let's define the function factorial, and we'll give it as input some positive integer, and we'll call that positive integer n. And so what do we actually want to do? Well, we saw before that we wanted 4 times factorial 3, and then we want to get 4 times 3 times factorial 2, and so on. But we can think of this as being a general process of really just computing n times factorial of n minus 1. And so that's what we'll actually just return. Because remember, we realized that 4 factorial is really equal to 4 times 3 factorial, which is equal to 4 times 3 times 2 factorial, which is equal to 4 times 3 times 2 times 1 factorial. And so I'm just going to comment this out so it doesn't flip out. But this is, we're trying to do that with this function. In this case, if I actually set n to be 4, then we would be doing, n would be 4, and we'd do factorial of n minus 1, which is 3, and then we would go further. But so what is this actually going to do? Well, let us suppose that n does equal 4. The function will first return 4 times factorial of n minus 1, which is going to be 3, right? And then what it's going to do for this factorial 3 is before it can actually return and print, the function will now compute factorial 3, which again we know is n times factorial of n minus 1. So now it's 3 times factorial of n minus 1, which is 2. And then this will have to be computed. So it will be 2 times factorial of n minus 1, which is 1. And then we get to here, and we get, okay, n will be 1, and so we get 1 times factorial of 0. And so this is what we described up here. In terms of basic math, this would be the computer program representation of this using this function. But we'd like to think, okay, great, we're done. But really, there's actually a subtle issue here, and some of you might have caught that. The issue is, when will this actually end? Because as far as we're concerned right now, it's always just going to return n times factorial of n minus 1. So this will really just go down to be 0 times factorial of negative 1. And then that will just go down to be, okay, we'll get negative 1 times factorial of negative 2. And this will just keep on going infinitely down to negative infinity. But that's obviously a problem. We can't just keep doing that. And we'll actually get an error. So if I get rid of this, or if I print this, so first I got to comment this out. So now if I run this, we're going to get an error. And let's see what that error is. So we get a range error because the maximum call stack size is exceeded, which pretty much means the program has run out of memory. So many calls to factorial have been made that the program just says no more. There's no more memory. Of course, there's not infinite memory. There's quite a bit less than infinite memory. And we got to it way too quickly because, again, we never end. This will just keep on being called factorial of -3, then -4, and so on and so forth. So how can we fix this? Well, in any kind of recursive function, we need a way to terminate. We need a way to actually end the recursive calls at a certain point. And we call this termination point a base case. And different recursive functions can have very different base cases. So I'm just going to say, again, we need a base case. And really, they are all just effectively some condition that the function will check each time it runs. And if the condition is true, then the function will not return another recursive call to itself and will instead give a terminating return, i.e. an actual value. So when would we want this function to stop? Well, in general, for factorial, when n is equal to 0, when we get 0 factorial, we just want 1. And that's when we end it. So we want this function to stop when n, the input, is equal to 0. So we can actually just check that. So we'll say if n is equal to 0, then we just want to return 1, because that's how a factorial works in math. This is our base case right here. Okay, so again, we're checking this every single time. So now let's go back through this. Again, I'm just going to get rid of these. So this is what we were describing as how the actual order of being called will happen. So we got all the way down here. We did 4 times factorial 3, got all the way down. Now we got to 1 times factorial 0. So now when we call this in here, at this point, after this recursive trail down, n will be equal to 0. So this is going to return 1. This is going to return a concrete value. So now the program can say, okay, we got 1, so we can compute this, and we get 1 times 1. So that's from here. So now this will actually return 1. And so now we have 2 times 1 for this call. And so, again, the program can compute this concrete value. So the factorial of 2 will return 2 after all this recursive calls. And then so now we have 3 times 2 from this factorial 3 call. And so 3 times 2 is, of course, 6. So then factorial 3 will have returned 6 after, again, recursively going up. And then now we got to the factorial 4 call, this original call right here. And so we get 4 times 6, which is 24. And so that's what's going to be returned. And we can check that. And that's exactly what we get. And I'll just, to show you this, every time we run this, I'm going to just print n, okay? And so this is what happens. N goes recursively down to 0, and then we get 24, going all the way back up. And it's because all these calls happen in that order down. The first actual computed value, as we showed down here, was factorial of 0. And then it went up to factorial of 1, and then it went up to factorial 2. That's what it means to be recursive. Like you kind of recursively go down, then recursively compute back up. So that's really how it works. So again, these inner calls, factorial calls, recursively called, will be executed before this actual print statement. This factorial of 4 will actually be the last computation. Factorial of 0 will be the first real computation because it will return 1, which terminates the recursion because there's no more recursive call to the function. All right, so hopefully that made sense. That's all we're going to cover today. Remember, really just the 2 points of recursion is that for any recursive function, you are recursively calling a function. Here's our recursive call. In factorial, we're calling factorial on n-1. In other recursive functions, you might have a very different recursive call, but in this case, we're just saying factorial of n-1, and we're multiplying it by n. And then this condition, if n is equal to 0, returning 1, this is our base case, right? This is what we're checking. We're saying, okay, when n is equal to 0, we want to terminate the recursion and return 1, and then we can recursively trace back up and actually compute with factorial 4. And that's what happened here. Remember, we went down, computed this 0, then went, returned them all back up. And that's when we saw, the 1 times 1, then the 2 times 1, then the 2 times 3, which is 6, and then the 3 times 4 is 24. And that's ultimately what we get, because that's when it ends. Cool. So thanks for watching. Please add any questions and comments below, and I'll see you next time.